Just a second, I have to arrange the screen.
Okay, we can see it perfectly. Amazing.
Just a second. Not so simple to have two screens here. So you don't see the one of the videos as I can see here. Okay.
Oh yeah. Oh yeah, this is nice.
Yeah, that's just for introduction.
Okay.
Okay, so it should work. Okay.
Yeah, yeah, this looks great.
Yeah, so I have just a few equations so you realize what it is, but I'm not going to talk about them at all. I'm just going to say they exist. I'm just going to show you projects I have developed the last years. So on the industry. But as a professor, I always take my students to the side if they want to. So that's good. Okay.
Amazing.
Okay, let me put this on just a second. I'm gonna do a playback here.
Do you need to show something slides or?
So I'm not gonna.
I can share the slides when we start to give an introduction on PSC.
So you're gonna have the initial slides. Okay, so I'm not gonna share. Is that okay? So I should stop sharing.
Yeah, please.
All right, I guess we can open the floodgates now and get this thing started.
Okay, hi everyone. My name is Carlos Mayorga. I'm an officer for the Peer Student Committee, and this is our fourth Peer Student Committee Industry Insight Series. Welcome everyone. Well, first of all, Piyush will give you an introduce about our Peer Student Committee here. And then I will introduce the speaker, and the speaker can start doing the seminar. Thank you for being here.
Thank you, Franco. Hello everyone, welcome to today's seminar on application of vibration monitoring and system identification to complex structure by Dr. Rubin. So before starting with the seminar, let me give you a short introduction on the Peer Student Committee. Our mission is to engage and empower the Earthquake Engineering Student Committee across peer institutions and beyond. We are dedicated to fostering a collaborative environment and driving impactful initiatives on three key fronts with research, professional, and outreach subcommittees. With the research and professional subcommittees, we actively promotes and supports earthquake engineering among students. We also host regular seminars and create platforms for undergrads and graduate students to expand their knowledge and expertise in their respective fields. With the outreach subcommittee, we strive to extend our knowledge and passion for earthquake engineering beyond the confines of our academic institutions. We also organize various outreach initiatives. We have recently launched the Pathway Initiatives, in which we connect undergrads and graduate students to their mentors in their respective fields. So currently we have 14 officers who oversee these three subcommittees. We encourage you to reach out to us if you have any questions or if you are interested in getting involved in any of our professional research or outreach initiatives. We are here to support you and guide you on a journey. And for more details about the specific events and the upcoming seminars, you can follow the LinkedIn page and also visit our website. You can also subscribe to a newsletter. So now, without any further ado, I would like to pass the floor to Franco, who will introduce today's esteemed speaker. Thank you.
Thank you, Piyush. Well, our next speaker is Dr. Ruben Boroschek. He is a distinguished expert in earthquake structural engineering, currently working or serving as a professor at the University of Chile. His research areas include seismic hazard assessment, structural health monitoring, and vulnerability assessment of critical facilities. He has also made notable contributions to the industry, particularly in structural health monitoring and assessment of industrial facilities. Dr. Boroschek has received prestigious awards, including the Engineer of the Year in 2017 and the Best Industrial Project of the Year in 2019 by the Chilean Structural Engineers Association. With his expertise, he brings valuable insight to the peer student committee Industry Insight Series. Thank you for being here, Ruben. The microphone is all yours.
Thank you. I appreciate the invitation to talk about what we have been doing in Chile, Peru, Colombia, and Central American countries, and sometimes outside the Latino countries, on this topic of structural health monitoring. I'm a professor at University of Chile of structural dynamics, so I always try to combine my company activities with our research activities at universities. So I'm gonna start showing here. Just give me a second to organize my screens. Just a second. Okay. Let's see, just 1 second. Okay. I think that will do it. Okay, so the idea is to show practical applications of vibration monitoring and some system ID. I've been working on this topic since my first instrumented building. I did it in 1982 in Costa Rica, Central America. And I've been instrumented structures since then. I did my PSC at UC Berkeley and have the honor to be in the experimental lab with Professor Godden and other colleagues there. So I learned a lot in that period and also in the practice. So I'm currently working on computer vision monitoring of structures, as you can see on the right. Let me put the laser pointer. But I'm gonna talk about mainly business application on this topic. So many of the things I'm gonna show have been developed initially by students and some professors of different universities in US, Portugal, and France, and Chile, and several engineers in my office. Just to understand why we do this in Chile, one of the things is that Chile is a quite high seismic country. If you check, for example, magnitude 5 that occur in a year, in a given year, I just collected the magnitude 5. These are generally produced at accelerations between 1 to 5% G or less, depending on the distance and soil conditions. But we have, as you can see here, nearly one every week and a half or so in a year, and magnitude 6 that are sometimes more closer to 5% G. Then we have one every 4 months or sometimes more than one in a month. But we don't design for this, except that we design for no damage on those low level for us earthquake, but actually we design for our extreme earthquake that we have plenty of those. So we have, if you only count the magnitude 8 that produce accelerations between 0.3 to 1.2 G recorded already, we have one every 15 years. We have a magnitude 8 with accelerations close to 0.4 Gs every 10 years. So, and we have, of course, we have the magnitude 9s that occur in Chile around 300 years return period. And we have already have like 10 or 11 of those in the last 4,000 years. So because of this high seismic activity, we teach at the undergrad level structural dynamics, experimental dynamics, and also seismic design, undergrad level. Okay, so all our students can at least know or have gone through half the book of Anil Chopra structural dynamics at the undergraduate level. So that's an important issue because most of our students understand structural dynamics, and also the main industry in Chile, that is a quite small country, so it's only 20 million people, is the mining industry, and we have a lot of issues with mining industry production, vibration due to machinery, blasting, and of course, earthquake. So we try to teach our students all the tools necessary for a professional life, including dynamics. Just a second. Okay, so this is examples of what we have done. So my idea is just to show what we have done at the experimental dynamics or basic dynamic class. So for example, a few years ago, we have this bridge in the center of the capital city, that is Santiago, and there was a building 11 stories, a 22-story building, and they want us to design the energy dissipation devices and stoppers that will accommodate the relative deformation of the two buildings. So the first things that I decided to my students on the dynamic class and just go into the bridge during construction and just allow them to jump on the bridge or walk on the bridge and have a very high sensitivity sensors. This is, for example, to monitor the transfer of motion or the vertical. And with that, we get a recording of the motion, and I teach them how to analyze these records so they can, let's say, get the basic damping or frequency or mode shape of the structure. And then we go and update a numerical model of the structure and try to simulate the relative vibration of these two buildings and design the shock absorbers. And I did this in 1993 or something like that. And already we have 2 designers going through this structure. That's a nice thing about living in Chile, that you test all your system on all your designs. And there was no, this is a glass bridge, and there was no crack in the bridge. But at least I can use the experimental dynamics to teach dynamics to the students. And this is another example one of my students did. So we have this is an undergrad student. So this is a 1 kilometer port in central Chile. And they wanted to increase the number of pipes and the number of conveyor belts. And the key issue here for this port was to understand what was the operational damping of the system. So if the damping was below 3%, they need to reinforce. If it was higher than 3% critical damping, they don't need to do anything and just build on it. So you cannot model damping properly, so we have to go and test. So I grabbed this graduate student, last name is Vega, and another professor, Baxler, designed a pooling system that we just anchor the system here, anchor the system here. This is a construction gap or just a dilatation gap for wave motion and construction and temperature things. So we put a 100-ton jack here. We pull the system and we put some, let's say, fuse system here, and pull the whole kilometer structure and abruptly release it and get the response of the structure. We have velocity sensors, accelerometers, deformation sensors, everything. We got the analysis of the signal. We do different type of analysis. This is a problem of initial condition with multiple mode shapes. In this case, you're seeing a time frequency decomposition. Very simple one could be a short time Fourier transform or more sophisticated tools. And we just get from this decay mode shapes and damping, and we were able to tell the owners of this port that the damping was below 3%, and they went into spend more than $10 million in retrofit it was starting the 2000 or something like that. So here a student was already collaborating with the industry, and this was a job that was required to the university. We also, in the experimental dynamic course, we do a lot of ambient vibration. So we teach how to analyze a signal from a high sensitivity sensor, let's say accelerometer or velocity meter. We're not using too much direct displacement meter, except for now video cameras that we do in ambient vibration using video cameras, but I'm not gonna talk about that. So we teach how to get the maximum response, the frequency content, and also the evolution RMS value or some characteristic of the time characteristic of the signal. And if you transform it to the frequency domain, we go through standard frequency domain identification, parametric or non-parametric, just picking for the frequency. For example, this record from this building, we just grab some students, put the sensors there, and measure the response and get the first mode and second mode, torsion, mode shapes, and damping of the system using very simple techniques, non-parametric, that you can teach in undergraduate course. And these are the basic formulas. Don't go through, I'm not going to go through them, but they are quite simple, and I can teach them at the undergraduate course. So, of course, when you go to the field on more professional base type of applications of system identification and vibration monitoring, you have to go to more complicated methods, and we generally teach them those at the graduate level. And the Society of Experimental Mechanics decided to do a handbook that is, I think, more than 1,200 pages now. And they asked me to write the civil engineering component of this handbook, and I did it with a colleague, Joao Santos. So we explained what was most commonly used in this area as applications, not as a research matter. So if you want to go in details on this, it's a good summary, but it's not the only one. There is a very good book from ASCE by Nekati Katsvas and colleagues, and it's an excellent reference, and many other books. You can go into this system identification methods. But I'm not gonna talk you about method, but actually applications. So I'm just gonna walk you through some examples of application, more or less using a reference of time. For example, Chile is a mining country, a seismic. So most of my work is in the mining sector, okay? So one of the most common type of analysis we do on the field is to evaluate the effect of vibrations on the human body. So in this case, for example, this is a very interesting project. There were a person walking on the mining processing plant, and actually he fell inside of one of the machines and died. And the question was why he did such a thing, why he was walking and fell into this ceiling screen that later caused his death. So this is interesting, a typical project in the high Andes. So the mine is at the level of 5,500 meters. So that's around 15,000 feet. So temperature, the maximum temperature is -5 or -10, and typical temperature is -20. So it's permafrost, and there was some, due to some reason, the temperature increased in the region, the soil was no longer permafrost, and everything was shaking too much. And we measure all the vibrations in order to evaluate the effect on vibration on the stability of the people. And in this case, for some reason, I'm going to go through it, we detected that the people that work on this facility were having resonance effects on the eye due to mechanical special machines that were there. And so there was a distortion of the sensations, and the coordination between body and eye was distorted, that we assumed that this was the cause of the problem. So this is, I think, the most common measuring technique that we use, just evaluate frequency content, amplitude, and correlate with standards that apply in each country. There are some ISO standard or American standard or whatever, and we try to understand the human response to vibration. This is the most common one. Another option that we have been doing a lot, actually, is in the high industry. You can see the size of these machines, it's humongous. And many of these machines are pretty heavy, and they induce strong vibrations in the foundation. So many times the foundations suffer damage, and they want to understand why the damage has occurred and how to repair or retrofit the foundation. So we usually go on site, put accelerometers, crack meters, and other type of sensors depending on the type of problem we're having. This wall is this one here. These are, I think, 2.5 to 3 meters thick, and these are like 8 meter thick walls. This is pretty big and massive structure. And what we do is to try to model the thing, understand the behavior, and recommend retrofit techniques based on some type of model updating, but very crude model updating that relates to deformations and some of the dynamic properties, but mainly stiffness related monitoring. So this is quite common. But we also do a lot of buildings. Actually, when I came back from my PhD from Berkeley to Chile, I offered the design office the possibility to validate their models in already finished buildings. So I arrived in 1992 to Chile. So I started to monitor the dynamic properties of most of the medium to tall buildings in Chile. So for us, medium height in Chile is 25 stories. I know that for the US, this is high, but for us, it's a standard building. Most of our buildings, tall buildings, office buildings, are between 20 to 40 meters, 40 stories. So what we do during this period with many offices was just to install temporary monitoring on each of these structure and just get the natural period and sometimes the mode shape of the structure, so they crudely correlate with their design. There was no model updating at all, because this is the 90s. Even if we knew how to do it, we can do some optimization techniques to optimize the model. Actually, the designers didn't have time to do anything of that, and they didn't understand at all. So they just want to know if they are missing the main periods by long, and if the mode shapes more or less is represented by the numerical model. And I did this for at least 10 years for many consultant offices, until they get so confident on their models, they never call me back. So we only do this now when there is a problem of vibration in some of the buildings. We keep working on very complex monitoring. For example, in this case, this is a spin-off of the University of Chile. So we did a lot of work for them until they got scared of the responsibility that we have doing some of these tests because of the people that we take. Sometimes we took students, it was not, they decided it was not safe enough. So after this type of projects, I decided to start my own company in the 90s. And this is, now we do it in the companies. But this is a huge tank, it's a buffer tank for high density liquids. And you see here a person installing accelerometers in the whole structure. So it's more or less this height here. And so the idea in this case, for example, this tank has different levels of liquid depending on the volume of processing in this industry. And sometimes it gets to resonate and the bolts on the bottom of this tank get loose. So they wanted us to know why they get loose. So it's a problem of resonance. But here we have many, many variables: the height of the liquid, the relative stiffness of the liquid to the steel wall, the velocity of the suspension helicoidal system that revolves around this liquid in order so it doesn't. It's sustained in water, so they need to be moving these tools around so to make the sand stay in the water. So density changes. So we were able to detect exactly in which combination of volume, speed of the motor, and the density of the material, the resonance occurs. So we can say, okay, don't be at that time for too long, so you don't build resonance. And this is how we solve this type of issues. So it's a mixed problem of monitoring, understanding all the variables, doing very complicated models, and then in this case particular, no change at all in the infrastructure, but only on the operational conditions of this type of system. And we use basic sensors, like in this case, only accelerometers to solve the problem. And this is one of the issues in our case, is that when you go into this type of monitoring on site, the risk for the operators, for us, is start to getting high, and then you realize you need, you cannot longer use any type of students or that has not been trained on how to operate many of this equipment. So from the 90s on, actually we have highly trained operators that are qualified to work in the high Andes and in very harsh environments, as I'm going to show you in the following slides. For example, in this case, again, mining, I'm going to switch from mining very soon, but just to understand, it's another problem of resonance in a structure. So in this case, for example, you see a machine that is part of a sieving, just to separate the size of grain, that is quite large. There are 15 of these, and the question was, okay, we want to replace these machines, but we need to understand what is the dynamic load on the supporting structure. This is like a 7-story structure, so we want the load, the combined load, the maximum load, the amplitude levels, and everything in order to, so we can replace for equipment that has a higher production, but not increasing the load, so we don't have to retrofit the system. You can see the dust level is here, is very high, so you need special equipment for monitoring, also for the safety of the monitoring people. So we have to be dressed especially, but many of these projects are about 3,000 meters, so oxygen level is very low sometimes, and you have to have a special health condition to operate in this condition. I'm quite happy that I'm able to work up to 5,500 without any problem, so I can do this type of job, but it's not so common. So you need to select the people in appropriate ways. So what we do here, we put, for example, accelerometers We do, again, a time frequency decomposition. I can explain this, how we do it later in the questionnaire part, just concepts now. And we get the intensity of vibration is the darker color here, so we get the resonance value, and from the decay we get the damping, and from the relative motions between the two surfaces of the spring we get the loads on the spring during resonance, for example. And we estimate operational loads for fatigue analysis of the structure, and extreme loads operational still for stress evaluation maximum, and then you add the seismic and the wind and the snow in order to do the modeling of this type of structure. So again, it's very simple, non-parametric things, but with the appropriate sensors to capture the loads that we need. In this case, the dynamic transfer load and the damping of the system for the analysis. Another mining project, it was very interesting. I have more than 400 projects. I'm not going to show you all of them, so don't worry. But this is a moving crane that is moving copper cathode. So these go into pools that have acid and electricity. So you get a pure copper plate here. So the problem here was that when this traveling crane that is pretty big, you can see here, I think this is 400 meters long. So it was moving too much on the rails due to deformations on the structure. So we installed several sensors on the traveling crane to detect where the irregularities of the structure generated motions on the crane. And some of these motions were so strong that some of these plates were released and fall. So in this case, we capture and detect the irregularities that produce the fall of the plates. And the solution to this type of problem is the stiffening the supporting beam and correcting the irregularities on the rail. And after that, everything was working okay. But the environment here is pretty nasty. It's actually acid vapors around, so you cannot be here too long. And sometimes if you go into the pool area that is now covered, you have to have a special rubber suit so you don't get burned. But those are projects that don't last more than a day or two. And it shows us, give us all the knowledge to do more complicated things. So I'm going back now to the 2010 earthquake in Chile, and it turns out that the area that was affected was a large area, 600 by 200 kilometers, with acceleration higher than 30% G. So we have 10,000 buildings, 12,000 bridges, and many other infrastructure. And at that time, Chile, a small country, and not too rich, actually, we are a developing country, had only 3,000 engineers, and it was impossible to review the damage in the whole infrastructure. So we start thinking, why don't we have a lot of sensors in the structure so we can prioritize the inspection, at least the location of the inspection on the system. But people on the industry keep us asking for temporary things, and we start telling them, okay, but we can do more than that. We can put the sensors and give you information when the foundation is changing or deteriorating and where is it happening, so you can have a predictive damage and maintenance instead of reacting to the system. But it didn't work out. This is one of the largest machines we have monitored. This is 40 meters in diameter. If I stand here, I'm here. It's very big, and this was opening, the walls were opening. These are more than 2 meters thick. But so they wanted to retrofit, so we put some sensors. They went before retrofit, after the retrofit, and we validated the retrofit for a period of 4 months. After that, we retrieved we actually didn't retrieve anything. We just left the instrumentation there, but we stopped monitoring. We didn't want to do anything else there. So I'm gonna go faster because I'm running out of time. But here is another building, interesting one. This is a 45 meter building that supports a crusher, a large size crusher. So it shrink rocks of 1 meter, 1.5 meters to centimeter rocks. And somebody did a small hole here to pass equipment from one slab to another one, and then the whole building started shaking a lot. So what we did at that time was to do a lot of monitoring, trying to understand the dynamic properties of the structure, reproduce the whole, then realize that why the building was vibrating, and do some retrofit and design the retrofit so the vibration stop. I'm gonna skip all of this. Okay, so we wanted to go beyond that. So now switching back to the university, and where you can think on longer times and have failure without having a problem with the owner or being sued because you did the wrong thing. So we instrumented a building in 2009, and we decided to do an online automatic structural health monitoring, meaning that we can detect any changes on the building continuously. So it is a very simple structure. It's a 9-story building with only 8 sensors, accelerometers, good sensors. AP sensors are high sensitivity sensors. And we monitor this thing since 2009 till now. And what we do is that every 15 minutes, we get an evaluation of the modal properties of the structure. And we have an automatic system that detects changes of these modal properties. And every time there is an earthquake, we also monitor the modal properties before and after and during. And also we evaluate the interstory drift and maximum displacement. So in this building, because we are in Chile, we have recorded 1,700 earthquakes. Yes, 1,700 earthquakes. And so we have a lot of, most of them are quite small. But one of the nice things when you have a lot of shaking is that you can monitor things like, for example, let's take here this image. This is the displacement of the roof as a reference. And this is the first mode period. And this is before the 2010 earthquake. So, and this is after. So the jump from here to here is damage, is 18 or 20% period change, meaning that during the earthquake, the stiffness changed around 40% because mass didn't change too much. So we detected immediately that there was damage, but we detected many other things. For example, the nonlinear elastic behavior of any healthy or non-healthy structure. And we can track now changes due to a small earthquake. All these little red dots are earthquakes in the same building. So we know that this structure after damage, when it has displacement, reference displacements, these are not drift. It's a reference type of displacement. It's in acceleration units. We can discuss that later. But it tells me that changes quite strongly as a nonlinear elastic response, and we have to consider that in order to develop a structural health monitoring system. That is a system that will tell the owner if the structure was damaged and hopefully where it was damaged. And we have done this not only in this building for research projects, but also in Peru for some heritage structures. This is a pre-Inca type of monitoring in the northern part of Peru. We did it with Catholic University of Peru. And in this case, for example, we tested it on the lab, which is the minimum damage we can detect on these walls, and doing some of this stuff. I'm going to skip this. And we had applied this as a research project in churches in the Cusco area in the High Andes, and many in 2 churches in the High Andes. But our goal is to go into the industry, actually. So our focus will be to instrument hospital, and this is the case of Chile. All hospitals that are base isolated, that are all complex hospitals in Chile, have to have a structural health monitoring system now. And dams that since 1960 has to be instrumented in Chile, all of them. Bridges don't have to be instrumented, or buildings don't have to be instrumented. Industry does. But what we want is a system, a structural health monitoring system, that instrument this with special sensors that will automatically capture the data, analyze the data, detect change of state, infer damage, hopefully the location of damage, and will alert the users in a way, in a language that they will understand by simple street light type of indications to numbers, or just direct instructions. Some systems already have some active system like closing a valve, stopping elevators and things like that. But the key thing for this to work is to be fully autonomous, no human intervention in any of these steps. So are we there yet? My answer to this is more or less. Okay, so can we do what I just said to inform the users or stakeholders on the state of health of the structure? One of the things we can definitely do is to detect a change of state. I mean, just monitor the structure, an event happened, and check if there was a change during that event. That, I think, is not too costly, not too many sensors, and we can do it. Can we localize the damage? Yes, but you need a lot of sensors and give a lot of scenarios to do that. Can we quantify the damage? Yes, or no, but you have to be right on the scenario, and you have to have a special sensor, camera, whatever, measuring, but because in general terms, you cannot get from global data the quantification of the change. And can you predict the remaining life? In our case, in civil engineering, no. In mechanical and electrical engineering, yes, because they have a statistic of the same damage in the same structures. We don't have exactly the same structure ever, so we cannot do remaining life for the moment. So we typically use accelerometers, expensive, cheap cameras, and now we're start using drones, but with very limited use due to some restrictions that we can talk later. So, okay, let's go now to industry monitoring, structural health monitoring. This is the construction of a 54-story building. So they ask us to get the model parameters of this structure and compare it to the design model in each stage of construction. So what we did is to install during the construction. Okay, it's a huge, this is a person here, this is one of them. So we install a system during the construction that will analyze the dynamic properties automatically for this building every 50 minutes, again, and use the construction vibration and the earthquake to give the properties of the building. And once a week, okay, so here's the evolution. For example, this is in month, okay? So you can imagine it's a one-story built every week, and we have 54 stories, so you get more than 54 weeks of construction. So what happens is you start monitoring the first mode. This is in frequency domain, and this is month. And so the first mode frequency decreases, so meaning that the period of the structure increases from 2 seconds or 1.5 seconds to 5.5 seconds, for example, in this window. And for all the modes, some modes appear very late on the construction because they don't exist, because it's the stiffness and mass of the system changes along the height. So the idea was, okay, this up to here is a standard structure health monitoring, fully automatic. But the idea was for the owner, he wanted to be sure that the model at the stage of comparison, that it was done once a week, agree with the constructed facility. So what you see here in red is the first mode, for example, of the final element model, but it's not the unupdated model. It's a structural model used for design, but cut at the level of the analysis and without strip of all the loads that don't exist due to operational condition of the finished building, and adding the loads that we have during that period of construction. So that is done once a week for nearly 2 years. And we compare the evolution. So as you can see here at the start of the project, let's say, we have a strong deviation. So here the construction was stopped and try to understand why this was this mismatch. We found the mismatch, and the designer, that we are not the designer, evaluate he changed the model to this condition and evaluate if it complies with the code, and if it was needed to do demolition, it was not needed. So we were able to provide this knowledge to the designer, and they continue and finish the building. We stopped monitoring on January 2010. Then the earthquake occurred in 2010 February, 1 month after that. But we have the full signature, the full characteristic of the building just 1 month before it got affected by the strong shaking. It was damage on the building, but we were able to identify and locate the damage that was quite minor, and there was no need for any repair on this building. And the owner was very happy because the building, when it was finished, was completely covered by special cladding and some expensive plaster, and he didn't have to remove anything in order to do the inspection. So he was very happy, and we keep monitoring this building till today, actually. We try to make this instrumentation massive, but actually it's very difficult because still we have a lot of problems. There is no black box solution software that can adapt to any conditions. Buildings are highly nonlinear. Conditions of operations of the building changes a lot, but also the owners don't understand the benefit, actually. And sometimes the cost, the initial cost and the maintenance cost is expensive. So the only country that I see that it has extensive use this commercially is Japan. Okay, there are at least 2 or 3 companies. One of them has published the number of buildings they have is more than 800 buildings with a structural health monitoring system. Okay, and there are many companies around the world now doing this type of thing. But it's still, compared to the stock of building, with the exception of Japan, I think is very little, and mostly I don't think it's because of the cost, but also the number of people that know how to do these things, and the owners that don't see or they ignore the technology, or they don't want the technology because sometimes they fear what can come out of it. So the last project I'm going to show in the only project I'm going to show in detail. Okay. Okay. This is a building here that is located here in the middle of mining project. And just a second, I have to there. So this building is here. You can see here is a steel building, 7-story, quite large actually. It did house 500 people during operation. And for some reason that I'm not gonna discuss, it shouldn't be here. It should be around here. But turns out that they were building a new structure here, but there was some problem here, and they got late for 2 years, and they want to expand the mine to this side. So they hire us to instrument this building and tell them if after every blast, they blast every 2 days at exactly the same time. And the blasting distance was 25 meters, meaning right there, to 1,500 meters distance, and the charge was very high. So the building was subject to pressure due to the blasting, but also vibrations at the ground level. So acceleration, for example, the largest acceleration that we recorded inside the building was 2 Gs, 2 times gravity in the horizontal direction. So it was actually, windows were blown out. There were some damage, and our work was to instrument the building and detect the damage, locate the damage, and give them drawings indicating where to inspect in less than 30 minutes after each blast. And they have a crew that will go and inspect where we tell them. Repair, if it was a diagonal failure or something simple, they will repair it immediately. And it was a serious, they will repair it and will take no longer than a day to repair. They have a special crew on site. They have a lot of money to do this. And during the blast, the people were taken out in buses, 11 buses. And after we said that it was okay and safe, they went back in less than an hour if there was no damage. Less than 2 hours if there was no damage. So this is the project that we won the prize for that. Sorry for the Spanish on this, but so how will you do this? Because this is something real, and there are people working on this building. It's a quite large building. So our idea, and it did work because we did this for 800 blasts without any failure on our prediction on the damage localization and the severity of the damage. So how we prepare for a project like this? So what we did is to have many models of the structure in different operational and environmental conditions. This is in the high Andes, so we have snow, sometimes 2-3 meters of snow. Sometimes we have earthquake, sometimes we have summer, sometimes we have frozen grounds. So we did many buildings and models, and we recorded blasting sequences. So we developed a fragility curve for the system and classify the damage based on the immediate occupancy, intermediate, or life safety. And we develop an automatic system, okay, that will track the modal properties and the stress levels in critical elements of different scenarios. This is a simplified model. And everything was automatic. So the blasting occurred in a minute. We already have all the input records in the cloud, and we have many models running in parallel, and to estimate damage probability. And from the data, we estimated the change of state and local changes of states. And we developed automatic report that will tell element by element the level of stress, and it will show automatically all of this in these 20 to 30 minutes. Limit was 30 minutes, and was sent via email to the crew on the ground. We were not involved with the crew on the ground, but what we were able to evaluate, we were able to show that this technology is ready for production. Of course, in this case, you need a lot of money to have a 24-hour engineer just looking at this, and many sensors installed in the structure. But for a mine company, this is nothing compared to the production. Actually, the production was increased for this mine because they thought, due to the limitations on this building that was administrative, hotel and a restaurant building, they have to slow the production, and they realized that with the system, we actually changed the blasting sequence, so it didn't affect as much the structure. So they were able to increase the blasting loads and have a higher production than predicted. So the guy that hired us got a huge prize, and we got a very nice prize from the Structural Engineers Association. After the 2 years, the building was so badly damaged, it was demolished, as you see below. And we have done this for ports also. This is a 2-year project trying to understand the effect of currents, scouring, overloading on simple ports, and impact due to burning. And we develop a special system that goes underneath the port, the wharf in this case, because in Chile, I'm sorry to say, but they steal all the sensors and computers, so we couldn't put anything that can be seen. So we did it underneath, but it was in the splashing zone. So we did everything waterproof and corrosion proof, and it lasted more than 2 years, actually. And this was done for the Ministry of Public Works. It was fun until they ran out of budget to sustain this. But it was very interesting. We were able to develop and learn a system of alerting and informing the Ministry of Health of overloading of the report based on statistical analysis of the response of the structure or the modal properties or the damping of the system or the mode changes due to the burden things. So in a period of 2-3 months, the data was good enough to have knowledge on how to set up the levels of alert and alarm. And this was given to the Ministry of Health for operational use. It was a very successful solution for a very difficult environment, not only due to the marine conditions, but also because of the risk of losing the instrumentation due to human intervention. And it turns out to be quite successful also, this issue. So I'm starting to finish. Sorry for taking so long, but are we there yet with full smart cities? So in 2019, The Economist, in World Economic Forum, says that in order to have a smart solution and sustainable environment, one of the key issues, number 22, was structural health monitoring. So are we there yet? And actually, if you go on the different countries, what we are is we are acquiring data from buildings. For example, California it has a lot of a strong motion network, one of them run by the state, very important. But they don't do online analysis and structural health monitor. They record the data, store it, and give it to people to analyze. It's not an immediate response and condition. For example, if an earthquake occurs, how much time you need. So there are cases, and I'm sure in California and other countries also outside the US have this system, but they are not massive. And I think it will go massive. So where we are using a structural health monitor, we are using it definitely in nuclear, liquid natural gas. In some countries, it's mandatory in dams. In some countries, it's mandatory in bridges and hospitals. But in general, in office buildings and residential buildings, no. Except with the exception of Japan, as I mentioned, that is a voluntary situation. And of course, we have many structures that are for research purpose. So they are not on the production line. So they don't have the economic risk of having liability due to the wrong information that has occurred. Okay, some companies have already gone broke because they gave the wrong information to structural health monitoring. And just to finish, I'm not going to go through that. I will leave this here. Why don't we have more, aside from the risk of doing this, liabilities, of course, is because still we have very little human resources. Structural dynamics is not taught commonly at undergraduate level. Actually, it's more at graduate level in most of the countries. There are no black solutions, and there is a lot of ignorance around, at the stakeholder and maybe low interest. You can see, I'm not going to go through this, I don't have time, but we can do that. There is a more detailed analysis was done by Coley some time ago, why we don't have more extensive use of SHM, but it's increasing, huh? It is working. So with that, I will leave you with this video I downloaded from the web a couple of years ago on the Boroschek. So I decided to monitor the bridge with a simple video camera, tracking features, tracking all the edges. So I have a time displacement function of that gives me the stream, not only the motions of points, or do a full pixel motion of the things, but I didn't talk about anything of this visual, but this is the main research now for me. And sorry for taking longer than expected. I hope I give an image of applications of vibration monitor on the field. Thank you.
Thank you, Ruben, for your wonderful presentation. I really enjoy that, and the connection between the academy and the industry is very great. I have I don't know if anyone of the attenders has any question here. They can feel free to unmute and ask Ruben directly, please.
Hi, everyone. Hi, Professor Boroschek. I have a question.
Go ahead.
So have you noticed difference in the natural frequencies in damping obtained, whether if the vibration was, if the test was monitor, just ambient vibration, forced vibration test, or an earthquake? Have you noticed like differences in the...
A strong difference. So the amplitude of the response is key on this. So if you have a small earthquake and large earthquake without any damage, of course, you get a notable change in period or frequency, whatever. Most chips doesn't change too much until you get damage, or you have or hit a new boundary condition, and then due to amplitude deformation. So yes, it's highly sensitive on amplitude. Our system, based on reinforced concrete or even steel structure in a soil, it's highly dependent on amplitude. If you want to detect small changes, if you want to detect strong changes, then it's easy to do it. I mean, so it's yes, high dependence on that.
Thank you.
That is not necessarily a viscous system, or and the modeling is not rate dependent and things like that. It depends on the structure, of course. If we have special devices, you get different answers. We have monitored some friction system, so you get a highly sensitive to level of response if you break the friction or you don't break the friction on the system.
Okay, I have a couple of questions from the chat. This is a question from Danilo. When you are identifying the parameter, how do you guarantee the identifiability of the parameters? In other words, how do you ensure the recorded information is enough to identify such parameter?
I try to have as many recordings as possible in different conditions. So this is not, I'm not gonna put my academic hat here. So you have a very limited time to be on the field. For example, if you go into one of these office buildings, they will give you an hour or two to just disrupt their operations. So you need to have enough data, and the word guarantee depends on what you say to the people. I mean, it's not too difficult after you get some experience to choose properly the sensor sensitivity, the sensor locations, and the number of sensors to get more or less a robust system. But if you have doubts, actually you have to request to the owner longer times and more instrumentation set up until you get a stable value. Now, is this a fixed value? Definitely no, because, for example, in buildings, we do notice changes if we monitor during operational hours, for example, in Chile, from 8 to 6 p.m., 8 a.m. to 6 p.m., and at night, because we don't have the human loads and other type of operational, we have higher water tank levels on the top of the structure, or the use of the elevator changes the period. So we don't try to put more than 3 decimals in any, never. Actually, we try to work with 1 decimal or 2 decimals if we are working on frequency. But so you just have to be careful on the time they give you, the importance of the data you are giving them, what's the conclusions or the sensitivity or the consequence. So because you are not going to do the extreme for all the projects. You just need to solve the problem the owner have, and not the things that you can imagine it will be so fun to do. And this is where you start changing from a university view to a more practical application. You need to solve the problem with the confidence that you can do it for the time they give you and the money they give you. So warranties are related to that. Okay, it's not a fixed condition. At the university, you want to be sure, but you have, because you have the time. Okay? Here, generally, time and money and the environmental condition. I show you some of the conditions are just horrible. You know, one of the acid environments we were, the maximum time for monitoring was 20 minutes. Whatever you get in 20 minutes was the maximum data you will get. So that's it. You give the warranty based on that.
Okay, thank you. I have another question from Danilo. In one of your applications, the real instrumented building, when identifying the damping period or period of the structure, how do you isolate the soil contribution from the building period damping? For the model shown, they are fixed at the base.
Okay, there are techniques to do this. I mean, to isolate both. But and you can have Safak, or there is some papers by Professor Safak, that is now retired actually from USCS, and Maria Todorowska on this isolation contribution. There are many techniques to uncouple. But let me tell you, if you start doing that for the practice, they will not consider it, because what they have is an integrated model of the soil and the structure. So it is interesting because you understand what is what. I mean, and I have a paper with Maria Todorowska actually on weight traveling through the building, so we can isolate what's happening in the building and on the soil. But when you try to explain to the industry this, they don't consider it too much. But for example, we just finished monitoring some wind turbines, and what we do is to monitor the foundation. These are very tall wind turbines, 80 meters, and a small foundation, 14 meters diameter, and things like that. So we monitor the foundation and the structure, the mast and the nacelle. So we at least we know the influence at the ground level of the rocking components and the transverse horizontal displacement. So we get if we get the mode shape or that condition, let's say we're looking for mode shapes, we know what's the contribution of that component. And the rotation component also, that is critical for very tall structures. So when you have a small rotation in an 85-meter tall windmill, then you get a lot of deformation on the top as a rigid component. So we monitor the foundation. So in some buildings, in order to validate the rigid foundation condition, we actually do a lot of intensive monitoring on the foundation level. So we get the in-plane by deformation of the foundation and the out-of-plane foundation deformation. Both of them, but you have to have that question because it takes a lot of time, okay, to do this. I don't know if I answered the question, but I did try.
I have another question from Luis Lin. What software are typically used for applying these algorithms?
Okay, believe it or not, I use MATLAB. I develop all the algorithms, okay, all of them, from structure, state identification to simple decasings. But there are software, okay? I'm not gonna recommend anything, but there is one that is used by companies. But if you go into this software, and there are some MATLAB toolboxes already available that are free. The software I'm having in my mind is quite expensive. The problem with this software is that you have to be an experienced user. I mean, you have to understand what you're looking for. You have to understand sensors and noise level in sensors. So at the end, one of the reasons about this black boxing is not here yet, is that if you go beyond just monitoring the period, okay? Because monitoring the period can be done by most of the civil engineers, okay? You just put a sensor, do a crude Fourier transform, and choose the maximum value. And if you're smarter, you do a Welch type of averaging of the frequency container, you get a very estimate. So we have many companies that do just period detection and amplitude detection, okay? And there are plenty of software for that. But if you really go into model updating, then you limit your result to very few commercial software and a lot of academic software. But my answer is there are. Just look for it. Toolboxes, free in MATLAB, you can find. And if you want to buy something so you can have help from the supplier, there are Italian, Danish, US software. What I don't like is the system that only uses Spirit for monitoring. There are a few companies now in the world that are just installing one sensor in the building and detecting a change of state based on period change. And it's very, very useful, okay? But I think you can miss some type of failure and give the wrong confidence to the system. So it's a humongous change if you at least have one sensor, humongous. But it's not all what you need. So be careful.
Okay, thank you, Ruben. Thank you again for your presentation. I think we don't have any other question here. Now Piyush will inform the winners of the Uber Eats vouchers that we advertise for this event. You can share your screen. Thank you.
So here are the winners for the Uber Eats voucher. Thank you for attending the seminar and look out for the emails to accept these voucher and use it. Thank you, Dr. Rubin, for sharing your knowledge on this specific topic. I hope it will be helpful for all the attendees and it will inspire further discussions and advancement in the field.
Thank you for the invitation. I hope it's a motivating subject and more people are work on these areas of experimental dynamics.
Okay, thank you. Bye, everyone.
Thank you. Thank you. Bye.
Hola Rubén, solo va a saludar.
Hola Ricardo, un gusto.
¿Cómo estáis? How are you doing?
Yeah. Fine, fine. Just
Cool.
enjoying. Just I'm
Yes,
fine too.
Yes, the
Hopefully that,
connection. Yeah. Thank you, Ricardo, for the
you-
recommendation.
Yeah, hope they understand what we are doing here.
Thank you. Bye.
Bye bye.